Thank you so much, and thank you all for coming. What a great place to have a conversation. I just love this theater. And if there's one point I could make right from the beginning, I think we need a lot more arts and humanities in this whole sort of communication and messaging about climate change. So we'll probably be slides and graphs tonight, because that's what I do, but really hoping that down the road we do a lot more arts around this. And part of this was a great, I just put this article up by Marina Schaefer, Schaefer. Just I really like that, excommunicates himself, right? If you really think the grass is greener, it just isn't. There's nowhere that's going to be safe from climate change, so we better start dealing with it at home. I would argue that actually climate change is the most significant grand challenge that humanity faces today, and I don't say that lightly. I say that after 30 years of thinking about this. And the reason is because climate change is going to make every other grand challenge that we face more difficult or impossible to address. So you might think that hunger, and specifically childhood hunger or food insecurity, is the most significant challenge we face, right? 1 in 5 children in America faces food insecurity every day, right? Growing that food to feed children in America and around the world is going to be more difficult or impossible, especially in the tropics, because climate change is going to lead to extreme heat, where it's going to be difficult to grow crops, and lots of big precipitation events that are going to wipe out those crops, making it more challenging. You might think that national security is the most significant grand challenge that we face, even more so today than a couple of months ago. But the Pentagon has been on top of this issue, and they've issued a whole series of reports over 2014 and 2014 identifying climate change as a threat multiplier. That's something that we really need to pay attention to. You might think that biodiversity is the grand challenge. Elizabeth Colbert has written a wonderful book called The Sixth Great Extinction, of which we are in the midst of right now. The Earth, during the last 600 million years, has experienced 5 great extinctions, mostly from cataclysmic events, including the extinction of the dinosaurs from asteroids. And we're now going through the 6th great extinction because of what human beings are doing in terms of changing land cover and changing climate. You might think that public health is the most important grand challenge, and really the air pollution that's associated with our burning of fossil fuels, the expansion of vector-borne disease like malaria and arboviruses northward from the tropics is being driven by climate change. So actually dealing with those issues are going to be more difficult. So I am by training an ice core paleoclimatologist and a geochemist. I drill ice cores and reconstruct how our climate has changed. I've done that around the world. So what you're seeing in the upper left-hand corner is actually a cross-section of an ice core. There's nice hexagonal ice crystals, but those blobs represent samples of the atmosphere that are trapped in the ice lattice as the snow densifies and turns to firn and then ice. So when we drill ice cores, we go to these flat spots on big glaciers. This one in particular is from Antarctica, this record. We go back in time, we pull up that ice, and then we crush it, and we can look at the trace gas content measured in the air bubbles, which tells us what the trace gas content of the atmosphere was at the time that snow was deposited. And you'll see this record goes back 800,000 years, and what I'm showing in blue is the changes in the carbon dioxide content of the atmosphere going back 800,000 years. We also can melt the ice and measure these things called stable isotopes of oxygen and hydrogen and get a measure of how temperature has changed over that time. And you can see I've plotted that record in brown. You've been looking at that long enough to see that there's clearly this rhythm, right? There's 8 glacial cycles that we've gone through over the course of the past 800,000 years. Here we are in an interglacial. That was the last glacial maximum when there was really low carbon dioxide and really low Antarctic temperatures. There was nothing living in New England then because we were covered by a mile of ice. All right, really significant climate change that's happened from this level of temperature and this level of carbon dioxide up to here. The other point I'd make is that carbon dioxide has never been higher than 280 parts per million by volume, right, for the last 800,000 years. And other paleoclimate records suggest that's the case for about the last 20 million years. So I've just kind of changed the axes here. So the CO2 concentration and the Antarctic temperature are lower. We started measuring carbon dioxide in the atmosphere in 1957 at Mauna Loa, Hawaii. And since that time, 1957 to the present, we have increased the carbon dioxide content of the atmosphere, equivalent to a shift that we see between a glacial and interglacial age. Right? We have already had a dramatic change, a dramatic impact on the climate system. That carbon dioxide has come from the burning of fossil fuels that has provided so many wonderful things, but the byproduct of burning carbon is carbon dioxide, so it's added this to the atmosphere. Why do we care about carbon dioxide? It's a greenhouse gas. It's just like a blanket that you put on your bed on a cold Portland night. That blanket serves to trap the heat coming from your body. Greenhouse gases trap the heat coming from the earth, right? We figured the physics out decades ago. So if we're not careful, we're going to end up where we're going. If we continue to rely on fossil fuels as our main source of energy, by the end of this century, we're going to end up with carbon dioxide, something on the order of 1,000 parts per million. That will lead to catastrophic climate change, and we'll tell you what that means when we talk about sea level rise and changes in precipitation. Next, if we work really hard and we invest in clean energy and energy efficiency, again, it's going to be a little bit more difficult over the next few years, but I have no doubt we'll prevail. It's just when we will prevail. We might be able to stabilize the carbon dioxide content of the atmosphere at 450 to 500 parts per million, which means there's some climate change we need to adapt to, but we likely will be able to adapt to it and maintain some aspect of the quality of life that we enjoy today. So I'm coming back from 800,000 years, coming back to the present. This is a graph going from 1880 on the left over to 2015. There's a plot of sort of global temperature increase over that time period. You can see there's places like the center of Siberia and Alaska that have warmed considerably. But if you look at the bar graph on the bottom, you can see this monotonic increase in temperature, right, since 1970. And we know beyond a shadow of a doubt that that warming has been driven by human beings. It cannot be ascribed to natural variation within the Earth climate system. It can only be explained by humans emitting greenhouse gas to the atmosphere. If you look at that graph, 15 of the 16 warmest years have occurred in the 2000s and the 2010s, right? Anybody who tells you, oh, there's a pause, don't worry about it, they're not really paying attention to the data. Now, 2016 isn't finished yet, but 2016 is likely to be way hotter than any other year on record, right? So you can see we're down here through October of collecting the data on the order of half a degree warmer than the warmest previous year of 2015. In part, that was driven because it was an El Nino year, but a big part of why it's way warmer than any other El Nino years is driven by global warming. Just a couple of other sort of big global pictures here. A lot of ice scientists pay attention, and climate scientists pay attention to the Arctic sea ice. Why do you care about Arctic sea ice? Because it's white. And that white ice reflects incoming solar radiation and sends it back out into space. It's kind of like the air conditioner for the northern hemisphere. You get rid of that ice, you expose blue water, that absorbs the solar radiation. The radiation also goes into the water, heats up the water, makes it way more difficult for the ice to form. So it really changes the energy balance throughout the Arctic. And you can see that we're on this long-term decline in the amount of Arctic sea ice. This is the minimum Arctic sea ice that happens at the end of the summer. And within the next decade or two, it's likely to disappear completely. This November, if you've read this, it's amazing. The Arctic this November is on average 35 degrees Fahrenheit warmer than normal. 35 degrees. It's like hot in the Arctic. And that's a big part of that is because the sea ice just isn't there to cool the Arctic. All right, so now I'm coming down to a much more local level. So we've looked at meteorological records from across New England, from the U.S. Historical Climatology Network, and there's many ways that you can talk about extreme precipitation. I like to talk about it in a number of events that drop greater than 4 inches of rain in 2 days. They used to be relatively infrequent, and now they're frequent. So this is the number of events per decade. So you see back in the 60s and the 70s and the 80s, you know, average for southern Maine, we had 2 to 3 to 4 of these events. Over the course of the past 2 decades, right, we now have 6 and 8. So a doubling of these events. And these are the big events, that, like the one that happened in 2015, that lead to big flooding. You guys are just getting sort of exposed to it, I think, in Portland. Southern New Hampshire has a whole suite of really big flood events that are being driven by these big precipitation events, which are also made even worse because we're also developing our urban centers and putting in more impervious surface, so there's more runoff, so there's more flooding. All right, and now here's the sea level rise record. So there's a couple of entities that keep track of all the tidal gauge data from around the world. They're at the bottom there. There's a permanent service for mean sea level, that's out of the United Kingdom, and then there's a NOAA's tides and currents. So all those dots represent the annual average of what sea level has been. So you all know, living in Portland, that you have big daily variations in the tide. So we measure that and we take these annual averages and that's what's plotted here. You can also see that there's a pretty strong 20-year cycle in this data, right, that's driven by the relationship of sort of the moon to the sun, right? You see this big cycle. So you never want to look at sort of sea level rise trends less than on 20 or 30 years, depending where you are on that. But here's a long-term trend, right? We see sea level rising on the order of 1.87 millimeters per year over the course of the last 100 years. Now, if you look just since 1992, and I picked 1992 because it wasn't one of these really low values here, or wasn't one of really these high values here. I wanted to get sort of a nice sense of where sea level rise has been over the last 25 years. You can see that essentially the rate of sea level rise in Portland has doubled over the course of the last 30 years, right? So the rate of sea level rise is increasing. Now, if you look at what's happening on a global scale, this is really consistent. That last number, 3.45 millimeters per year. You can see that the long-term average on this, 3.4 millimeters per year. This is a data globally collected by satellites, TOPEX and JASON satellites, and this is data that's all been analyzed at the University of Colorado. The different colors represent the different satellites that have collected the information. They've done a lot of work to make sure that the records actually fit together. But you can see long-term trend, but the satellites only went up in 1993, right? So we've already seen this doubling of the rise of sea level around the world, and that's exactly the same rate that Portland is experiencing right now. There's places to the south of here, Boston and Maryland, that are in way worse shape because their coast continues to sink. It's called coastal subsidence. Portland, Portsmouth aren't experiencing that so much, so thank your lucky stars, we're not as vulnerable as some other areas. All right. So what causes sea level to change? I mean, I could really talk about this literally for hours. I'm not going to. Just briefly, thermal expansion. When the water warms up, it's less dense. It's less dense, it occupies more volume. So the oceans are warming up, and they're not just warming up the surface, they're warming up down to 7, 8, 900 meters, 1,000 meters. We're measuring that now. We're capturing that. So we're seeing sea level rise due to the fact that oceans are warming. And in fact, most of the heat that's being tracked by the carbon dioxide is now going into the ocean. The one that I have covered there is what I'm going to talk about a little bit more in a few slides. So glaciers that are on land, right? When they melt, they transfer water from the land into the ocean, and they cause sea level to rise. There's a few other reasons. The other one that I think that's pretty important here is a dynamic component. As we change circulation in the North Atlantic, we expect that actually that will result in higher sea levels on the eastern seaboard. Not unsubstantial, on the order of 6 inches to an additional foot, but they are really hard to project. So let's talk a little bit about glaciers and ice sheets, right? Greenland holds the equivalent of about 20 feet of sea level rise. It's a lot of water. It's a lot of water locked up in Greenland. And what we're seeing now is this dramatic shift in the behavior of the Greenland ice sheet from being relatively stable, maybe thinking it's something that might melt over centuries and centuries, to behaving like, sorry youth, I just got to say it, like a 18-year-old who just got the keys to the family car and has a six-pack. It's just starting to behave in a very strange manner to the point where it is beginning to disintegrate. What's really interesting for scientists is we've never seen an ice sheet disintegrate. So we don't really know how it happens. We don't really know how fast it happens. But for Greenland and West Antarctica, that's what we're beginning to see right now. So what you see here is this picture of Greenland, and the nice colors on it represent the surface velocity of the ice on the Greenland ice sheet. So we've done this by using synthetic aperture radar, looking at crevasses and seeing how those crevasses move. And I just want to focus in on this area right here called Jakobshavn, which is a really big outlet glacier that drains a huge part of the central portion of the Greenland ice sheet. And you can see when they did this research, it's moving on the order of 3,000 meters per year. 3 kilometers per year, a glacier that's the size of something that would flow like from Mount Washington down through the Merrimack River Valley. This huge body of ice. So this is just the snout of the Jakobshavn Glacier. You can see the retreat over the course of time, right? Here's where it was in 1851, this big ice tongue that floated out into the ocean. It came back, but it kind of stabilized, right around here, 1964, 2001. And then really as a result, both of surface melting, but as a result of warm sea surface temperatures, we've seen this dramatic retreat, and there it is back in 2010. And so as this ice moves out, this is like the cork in the wine. If you think about a wine bottle on its side with a cork in it, right? This ice was the cork keeping the ice up on the ice sheet. When you pull that cork out, right, the wine's going to flow out. So as this disappears, all of this ice that drains through this fjord is now flowing down. So how do we know that? So here's the data-rich graph. You can cross your eyes. You don't really have to look at it too much. But what it represents is the surface velocity of Jakobshavn Glacier from inland going up to the snout, essentially. So if you just look at the red and yellow lines, that's the speed at which the glacier has been moving from 1990 out to 2014, right? And again, this has all been measured with synthetic aperture radar because it's way too dangerous to walk on this glacier. So you can see down here, right, it used to be moving at 4,000 meters per year, 4 kilometers per year. It kind of went up to 8 in the 2000s. Now we're up around 12 to 14 to 16 to 18 kilometers per year, right? And that rapid increase in the flow of the glacier is because that cork has been taken out. All of that ice tongue has been removed because of those warm sea surface temperatures. So we've seen a 4-fold increase in the rate at which the biggest outlet glacier in Greenland is dumping ice into the North Atlantic. The same thing's happening in North Greenland, and the same thing's happening in the West Antarctic ice sheet. I want to tell you, in 1990, there was no glaciologist that predicted this. This has taken the glaciological world by storm. There's a big meeting right now out in San Francisco called the American Geophysical Union, and there's all kinds of glaciologists trying to figure out what is the mechanism. Is it going to increase? Is it going to slow? Is it going to stay the same? But there's considerable concern that what we're seeing is the beginning of the disintegration of the Greenland ice sheet. So again, Greenland is the equivalent of 20 feet of sea level rise. West Antarctica is the equivalent of 20 feet of sea level rise. It's going to take decades to centuries for these things to melt, but not millennia. I just encourage you to Google this. James Blaylock is a National Geographic photographer who sat up here and watched as this glacier disintegrated, sort of an iceberg the size of Manhattan Island. It's an amazing piece of photography. All right, so what does that mean for sea level rise, right? So scientists have looked at these glaciers around the world, and we're trying to project how high sea levels might change in the future. It's sort of the holy grail of glaciologists. And it turns out that to the first order, we don't really know, right? So, and I think by looking at this graph, this comes from the National Climate Assessment. We've used this as part of our planning for what we're going to do in New Hampshire. But you can see that there's 3 different scenarios. There's an intermediate low scenario where sea levels go up by 1.6 feet by 2100. There's an intermediate high where sea levels go up by 3.9 feet. And there's a high where sea levels go up by 6.6 feet by the end of the 21st century. Nobody in the science community believes that this is going to happen. This linear trend continues. That's the 3.4 millimeters per year that I showed you before. So there's a big difference between what society does in terms of 1.6 feet of sea level rise versus 6.6 feet of sea level rise. And the reason there's such a large spread here is because we don't know what Greenland and Antarctica are going to do over the course of the next 100 years. So that's a huge challenge for anything that you do, right? We don't really know how much sea level is going to rise. What we did for the New Hampshire Coastal Risk and Hazard Commission is we said, let's not worry about if you're building an oyster shack on the beach. Let's worry about really important infrastructure, wastewater treatment plants, schools, roads. If you're building something where you have a very low tolerance for risk, you should plan to build that to 4 feet of sea level rise by the end of the century. And in fact, if sea level rise happens more quickly, you should be prepared to ensure that it can deal with as much as 6 to 7 feet of sea level rise. But you begin to sort of sense the scale of the problem. We put it in that risk perspective in New Hampshire. Here is a statement in which there is no uncertainty, right? Sea levels don't stop rising at 2100. Sea levels are rising, and they are going to continue to rise for centuries. Generations of people are going to be dealing with this problem. So when you think about the solutions for the Bayside, don't think you can solve the problem in 50 years. It's going to be a continual effort at adaptation if we want to maintain those areas where we have infrastructure. And if that doesn't work, well, maybe we pick up and go somewhere else. Luckily, there's some places in Portland where you can go. But these are some pretty significant big questions. With 37 recommendations we just came out with, a couple of weeks ago for our New Hampshire Coastal Risks and Hazards Commission. I would really encourage you to have a look at that. That was a 3-year process involving 38 people, municipal representatives, state representatives. We had a climate skeptic on it. I mean, we really took a long time to come up with a guideline, a set of recommendations for our coastal communities and our state agencies on how to deal with that. But what I think came out that was really valuable are these guiding principles that you might think about using, right? So there's a notion that you need to act early, which means you need to start planning now. You can't wait 20 years or 30 years and 40 years and think you're going to have the money to deal with a problem that is this big. You need to start doing it now so that you can spend money year after year after year after year to address the issue. You want to respond incrementally. You don't want to deal with 6.6 feet of sea level rise right away. You want to wait to see how much sea level is going to go up. So you want to respond incrementally, but ensure that those incremental responses can be built upon in the future. You constantly want to revisit the science and revise what you're doing. This meeting tonight, I think, is a wonderful start. This notion of collaborating and coordinating. Portland government, that's great. This isn't meant for you, but don't rely on your government to solve this problem. We need to solve this problem. Government's one part of it, but businesses, individuals, other institutions need to get engaged. Incorporate risk tolerance in design. That was sort of that, right? If you're going to build something important, think about making it resilient to 4 to 6 feet of sea level rise. And all along the way, make decisions that are no regrets, that ones that just make sense for your community or the flooding that you're experiencing today. All right, we're getting to the end here. This is part of an image from a report that I wrote back in 2009 for Curtis Boland for the Casco Bay Estuaries Project. So we looked at a number of different scenarios for sea level rise. And there's been a number of different maps that have been developed. Sam, you probably have a set of maps not unlike this. The Natural Resource Defense Council of Maine has a set of maps. But they're all kind of pretty similar, right? So hopefully you've identified yourself. So here, this is a big storm. We get like a superstorm Sandy that hits the coast. So we have this big storm surge that Portland has experienced in the past. And I'm adding 4.6 feet of sea level rise. So that's the intermediate scenario, right? So you look down here and you see how vulnerable, right, this whole area is. You see the definition of Bayside, I think, is outlined pretty clearly here. And then you can see the inset here, right? So this is, all the blue here represents more than 1 foot of water. So this is you think about all those basements. You think about all that flooding, and there's really, right, nowhere for that water to go, right? It's coming from here. And so this is your big significant challenge. But it's also, this is 4.6 feet of sea level rise. This isn't likely going to happen tomorrow. This is something that's like middle century or end of the century. So you have some time to deal with it. But what you don't want to do is, I would argue, is engage in a whole bunch of building that makes it even more vulnerable than it is today. As you move forward, as you build roads, as you build commercial residences, as you build homes, you want to think about how you make this area more resilient, not more vulnerable. And that's going to take lots and lots of hard work. So I just wanted, if that wasn't bad enough, right? It's like, God, now you're going to talk about extreme precipitation. I showed you about those 4-inch precipitation events. So there's a map of all of New England, historical 1980 to 2009. And now what I'm plotting here is those 4 inches of precipitation events in 48 hours per year. Right? So 0.5 to 1 per year in the historical record. So 5 to 10 per decade. Right? Next slide. As we look at output from global climate change models and we downscale that to New England, this is 3 different global climate models. You can see that, right? Gulf of Maine coast is in the bullseye in terms of the increase in the number of extreme precipitation events. Why is that going to happen? Because the air is going to be way warmer. There's going to be way more evaporation. So that warm air is going to hold a lot more water. So when it rains, there's going to be way more water to come down, right? It makes complete sense physically. But so we're looking at more than 2 events per year. So we're going from half an event to 1 event to 2 events, right? A doubling to a quadrupling of extreme precipitation events. If we just use the same old conventional development and pave stuff, so all that water runs off, it's just going to make the flooding way worse. Not unlike what you had in 2015 with the cars floating around in the parking lot at Whole Foods. We're going to talk a lot more about probably specific solutions next, but just in the broad sense, we really have to think about both about mitigation and adaptation. So mitigation in the climate world is reducing the amount of greenhouse gas emissions, and adaptation is adapting to those changes. The single most important adaptation strategy is mitigation because it reduces the amount of change that we have to adapt to, right? So unlikely to get federal government leadership on that front. We need to keep leading on that front. It's really going to come from cities and states and individuals. And I would argue on my optimistic days that climate change is the innovation opportunity of the 21st century. We are not going to solve this problem with business as usual. We need to think in completely new ways about how we produce energy and how we use energy, and as you'll hear later, how we actually develop our cities. I would argue that we have to have a price on carbon. Again, that's unlikely to happen in the near future, but eventually that will happen because we need to somehow actually change behavior, and the best way to do that is via a price. We need to promote energy efficiency and renewables. We need to conserve ecosystems, especially across New England, right? We have all these forests there, this huge sink for carbon. Doesn't mean we can't cut down trees and have an active forest industry, but we need to ensure that that land remains available to grow trees. And also in our agricultural soils, we need to start thinking more about how we store carbon in those. And what we're going to talk about tonight is we have to adapt to unavoidable climate change. So, sometimes people call me Dr. Doom. You can see why. But there's also days that I love to dance. And the storm clouds are upon us. And it's not going to help to stick our heads in the sand, or maybe we should talk about sticking our heads in the water for the future. But the storm's not going to pass. It's here, right? And so we really need to learn how to dance in the rain. And I hope that this is the beginning of a really fruitful discussion that Bayside Adapts has, so that you are a resilient city, a resilient part of a resilient city that moves forward and is vibrant into the rest of the 21st century. Thank you.